Hey everyone. So today we're going to hear from Deepak Vasisht. He's a PhD student from MIT working with Dina Katabi. And he's done a lot of amazing work on mobile computing and IoT and from very different aspects from in body and just he's also been in the FarmBeats project where, it's such a big project deployed in many countries. And his work has been recognized in several articles, like in BBC, MIT Daily, IEEE Spectrum. He's won the ACM Sitcom Best Paper Award, and he's also won the Microsoft Research Fellowship. So without further ado, let's welcome him.
Thank you, Shad. Hi, everyone. I'm Deepak from MIT, and today I'll tell you about my work in building IoT systems. For a few years now, we've all been excited about this vision of the Internet of Things. IoT takes computing and embeds it into the physical environments around us. Imagine a network of devices deployed in a city that can monitor and regulate traffic in real time, that can tell you where the empty parking spots are, and that can help identify and control sources of pollution in cities like New Delhi and Beijing. Think about a network of sensors deployed in farms in remote rural areas that can help farmers grow more crops while being more environmentally sustainable at the same time. And think about tiny devices that can travel through your bodies to deliver drugs at precise locations, that can help with treatments of diseases like cancer and even perform in-body biopsies. This is actually a very exciting vision. And in fact, you've seen a lot of interest in this vision in recent years. In our homes, we see smart devices like smart bulbs, smart thermostats, smart TV, smart fridge, etc. And in the industry, we see a lot of investment from existing companies like GE and Ericsson and new companies like Samsara to develop connected sensors for industrial workflows. So the key question that I'm going to ask today is, what does it take to go from these individual connected sensors to this vision of the Internet of Things where IoT systems are deployed all around us? And to do that, we need to be able to solve three major limitations. First, and probably the most important, is that IoT devices today are limited to resource-rich environments that have easy access to power and connectivity. If I buy a smart thermostat today, I can plug it into the wall for power, and I can connect it to the internet using Wi-Fi or LTE. But the true value of IoT lies in environments where we do not have such luxuries, where we do not have easy access to power and connectivity. For example, in space, underwater, in forests, in remote rural areas, and even inside our bodies. Inside our bodies, for example, these devices are really tiny, so they cannot carry large batteries to power themselves. And even if you want to communicate with these devices using radio signals, these signals bounce off your bodies. The second limitation is that IoT devices today do not really understand their context. So if I buy a smart light bulb today, I have to control it manually, either using an app or using a voice assistant like Amazon Alexa or Google Home. But as we have more and more of these devices around us, this approach of controlling them manually does not really scale. Ideally, we want to build systems that can automate these decisions based on contextual information. For example, we want to build smart homes like this, where we have, let's say, two individuals, Alice and Bob. If Bob walks out, sits on the TV couch, the TV should turn on and tune into their favorite TV channel. And later, if Alice walks out, the home should realize that and reduce the light in the rest of the home to save energy. And we can build such systems if we can embed contextual information like the position and identity of smart homes into the design of IoT systems themselves. And finally, IoT environments today have many different types and kinds of sensors in the same environment. And yet we treat them as independent, isolated data streams. Ideally, we want all of these different data streams to come together, all of these modalities to come together and collaborate and cooperate for higher level sensing tasks. In this talk, I'm going to talk about my research in building IoT systems that addresses each of these limitations. I'll tell you how we can extend IoT systems to resource-starved environments, how we can embed contextual information into the design of IoT systems, and how multimodality can enable new kinds of IoT system designs. Specifically, I'll talk about my work in building in-body networks, about my design for context-aware smart homes, and I'll very briefly touch on how multimodality can enable data-driven agriculture. In building these systems, my goal has been to enable ubiquitous IoT systems that can be deployed all around us. And my approach has been to design end-to-end holistic systems that can integrate all insights from all levels of the computing stack, right from the hardware and communication layer, all up to the software, inference, and application layer. Specifically, my work has made the following contributions. I built the first system for communication and localization of deep tissue in-body implants without requiring them to transmit any power of their own. I also built the first system for accurate Wi-Fi localization of Wi-Fi devices using just one Wi-Fi access point. In contrast, past work required 3 to 4 access points for the same level of accuracy. And then I augmented the system with a reasoning framework for position and identity of occupants in the smart home, even when these occupants are not carrying their smartphones on them. And finally, we built this system called FarmBeats, which I'm assuming you're familiar with. It's a large-scale data-driven agriculture platform which has pilot deployments in multiple countries today. In the interest of time, there are other parts of my PhD research that I'll not be able to talk about today. Specifically, my work has spanned wireless networks and IoT applications. In the wireless networking space, I've worked on channel prediction for LTE networks, basically making the next generation of cellular networks more efficient. In localization of low-power Bluetooth devices, and in the IoT application space, I've worked on smart city networks and on building virtual touchscreens in the air where you can interact with your devices just by gesturing in the air. So let me start by talking about in-body networks. And before I tell you more about this work, let's take a step back and try and understand why we care about these networks. We care because the field of medicine around us is changing, and a lot of those changes are happening because of devices that can be embedded inside our bodies. For example, take these tiny capsules. You can swallow these capsules. They can go through your GI tract and take pictures. A doctor can look at those pictures and see if you have a disease or an ulcer or a tumor. So for these capsules, you want to be able to communicate with them. You want to see the data that they're sensing. And you want to localize them. You want to locate where they are when they're taking the picture so that you can program primitives like, deposit this medicine in the stomach or take more pictures in the small intestine. And this is just one example. There are more such devices. For example, micro robots that can do drug delivery or perform in-body biopsies or small markers that you can embed in cancer tumors for radiation therapy. And for all of these devices, we care about communicating with them, and we care about localizing them inside our bodies. But as I told you before, these devices are very power-starved because they're very small. They cannot carry large batteries. So what this means is that we cannot use existing communication technologies like Wi-Fi or LTE because they're very power-hungry. Think about our smartphones, for example. They use Wi-Fi and LTE. They have huge batteries, and almost half of those batteries is meant for communication alone. So ideally, we want to use something that is very low power, ideally something that does not require any power budget from these devices. And one way to do that is to use signal reflections to communicate. And on a high level, this is how it will work. So let's say there's this device that I want to talk to, this capsule, and there's a reader that's outside the body. So this reader transmits a signal, and just by modulating this reflection, by reflecting the signal back, this device can communicate bits of information. So this is not something new. This is a principle called backscatter. I'm sure a lot of you have heard this before. We've seen this in RFIDs, for example. But the question that I'm going to talk about is, what does it, can we take this backscatter principle and apply it in body? And as it turns out, it's not as straightforward. And in the rest of this talk, I'm going to tell you what challenges arise when you try to do this backscatter for deep tissue implants inside the body, and how we can solve these challenges to build this system called Remix that can do in-body backscatter communication and localization. So let's start by talking about communication. So this time, I'm going to put this capsule inside the body. And again, like before, we have a reader, and this reader is going to transmit some signal. But this time, most of the signal is just going to reflect off the human body. And only a tiny portion is going to go inside. And even this tiny portion that gets inside is attenuated further as it travels to this capsule. It attenuates actually exponentially. And this is how wireless signals behave differently inside the body as opposed to outside. In air, when we talk about attenuation, it is polynomial. It's d square or d cubed with distance d. But in body, it's exponential. And what this means is that by the time the signal goes back and gets back to the reader device, it is 100 million to 1 billion times weaker than the reflection from the skin. So the skin acts as a huge interference for the signal coming from inside the body. So this is what we call the dynamic range problem. There is this huge reflection coming from the skin, and we are interested in this tiny reflection that's coming from the target. It's actually not to scale, because if I draw it to scale, you'll not be able to see it here. So this is actually very challenging. Like, think about someone shouting in your ear with a megaphone, and you're interested in this whisper from a distance far away. We cannot do that. Yeah?
Deepak, are you talking specifically about a certain frequency range, or saying in general across a wide range of?
So this number 100 million to 1 billion is for a specific frequency range. It is about like 900 or like 800 megahertz or something. The higher you go, this number becomes larger. The ratio becomes larger and becomes like completely impossible to get any access signal from inside the body. At lower frequencies, this number becomes smaller, but the devices become larger just because like the wavelengths are larger. So you can't really operate at lower frequencies for in-body devices. Yeah. Okay. So our goal is to separate these minute target reflections that are coming from devices inside the body from these huge skin reflections that are being reflected off the skin. And to make this even more interesting, we want to do it with zero transmission power. So we don't want any active components inside the body. And our idea is to use signal circuit nonlinearities. So if you don't know what nonlinearities are, don't worry, I'll just tell you in a little bit. So typically, when we design wireless circuits, we program them to have linear behavior. And what this means is that if your input is x, your output is alpha x. So if you transmit a sine wave at the input, you get a sine wave at the output. It's as simple as that. But sometimes, because of imperfections, these systems can have nonlinear response. And what this means is that if your input is x, your output is a polynomial which is not linear. So it's alpha x plus alpha 1x squared. So if your input is this sine wave, your output is this distorted signal. So clearly that's undesirable because it causes distortions in the signal. But in this case, we realize that we can use these distortions to separate these target reflections from the skin reflections. And let me show you how. So we have this device inside the body, like before, but this time I'm going to transmit two signals from outside at different frequencies, frequency f1 and frequency f2. And then I'm going to make this device nonlinear. So like before, the skin reflects these signals back at frequency f1 and f2. But this device is going to do something different because I made it to be nonlinear. So it's going to create nonlinear combinations of these signals. And let's say it creates this nonlinear combination cos f1t plus cos f2t whole squared. And let's try to expand this term. So I transmitted cos f1t plus cos f2t. I got alpha 1x plus alpha 2x squared. If I expand this x squared term, I get cos square f1, cos square f2, and 2 cos f1, f2. And by basic trigonometry, if I expand this term, I can get cos f1 plus f2 and cos f1 minus f2. So notice what I've done here. I took a signal at two frequencies, f1 and f2, and I created new frequencies out of this signal, f1 plus f2 and f1 minus f2, which are combinations of these by using this principle of nonlinearity. And now I can shift these target reflections away from the skin reflections in the frequency domain. So the skin reflections are still happening at original frequencies f1 and f2, but these target reflections are happening at linear combinations of these frequencies. And then I can just filter them in the frequency domain to get rid of the skin reflections altogether. So the only question that remains is how do we create these nonlinearities? And as it turns out, it's fairly straightforward creating these nonlinear, because a lot of the effort in wireless systems is on not creating these nonlinearities. You can just use simple devices like a Schottky diode to create these nonlinearities. They're simple and small. It's passive, requires no power source at all. And interestingly, it's very highly nonlinear, so we can use it to our advantage. And by doing that, we can shift. Yeah.
Just I'm curious.
Yeah.
So you create these nonlinearities, but you still assume some regularity in the signal, right? For example, when you said cosine,
Yeah.
blah blah blah. So you're actually creating something like that. So what about nonlinearity in that itself? You know, like,
Yeah.
are you getting a cosine signal out of it, or something there?
So I think that's actually a very a very good question. I'm surprised you asked that because you just walked in. But yeah, so essentially the question is that what happens to the nonlinearity of the original signal itself? Because the original signal will have some nonlinearity, it'll like reflect off the body, and it'll still have that. So a lot of the effort in engineering for this project actually goes in making sure that that signal is regular. And one of the maybe I'll just walk back a slide to show you so here one of the things that we do in the system is that we separate the sources of both frequencies f1 and f2. So the original nonlinearities are at 2f1 and 2f2, but the cross products only happen inside the body. So we rely on the cross products a lot more than the nonlinearities of the original signal. Okay. So we can use these nonlinearities to isolate signals from inside the body in a passive manner. Now, the second part of this question is the localization part. So I showed you how we can get access to signals from inside the body. Can we use this signal to localize? And typically, the localization of these devices is important for many applications, like targeted drug delivery or guiding robots inside the body, or for cancer radiation therapy. And for all of these applications today, the main method of choice is either X-rays or CT scans. As we know, because these technologies happen to be expensive, and also they're potentially dangerous to the human body. X-rays cause mutations, which are not really helpful for the human body. So can we use the radio signals that we just extracted them out? And again, there's a lot of work in RF-based localization, a lot from here and also from other places, that talks about how we can locate these devices using radio signals. So typically, this is how it operates. So I can use this reader to compute an angle that the signal is coming from, and I can do it from multiple vantage points and intersect these straight lines to identify the location of this device. This is a simple principle called trial iteration. So what changes inside the human body? And to see what changes, let me take you back to this picture from high school physics. So when we try to look at things inside water, they appear at different locations than they're actually at. And this is because of a simple principle called refraction. Light waves bend when they move from one medium to the other, and as a result, you have this phenomena called refraction. Electromagnetic waves, like light waves, RF waves like light waves are electromagnetic in nature, and they bend at the interface. So they're going to bend at the interface of the human body. And they're going to bend when they travel from air to the human body. And this is actually a simplistic representation of the human body. If I zoom into this portion here, I'm going to see multiple different kinds of tissues, say skin, fat, muscle, colon, and each of them have different electromagnetic properties. And as a result, these waves are going to bend at each of the interface. So it's going to bend from air, skin, fat, muscle, colon. So if you use this existing model of localization that propagates signal along straight lines, you're going to get a wrong location for this device. So anything that's in the stomach might appear to be in the colon or in the liver. Clearly, we don't want that. So we cannot use these existing localization models. So we have to move from these straight line-based models to spline-based models. And splines are a sequence of polynomials. In this case, they're a sequence of line segments. And we have one line segment for each tissue type, one for skin, one for fat, one for muscle, one for colon. But this makes the problem a lot more complex, because I don't know exactly what's the order of these tissues, what's the type of these tissues inside the human body. And to make it worse, it's different for every individual. It might be different for me, different for you, different for everyone else. So we want to design an algorithm that does not have access to this information a priori, that's blind to this tissue composition, because this is going to be so different for everyone. And two observations help us here. One is that for the purpose of radio signals, we can categorize these tissue types into two major classes. One class of tissues that's based on oil, for example, fat, colon, breast, muscle, or like bone marrow. And all of these tissues have radio properties that are very similar to oil in nature. And the other class of tissues that are based on water, like blood, muscle, skin, cornea, all of these tissues have properties very similar to water in terms of radio signals. So we can cluster these tissue types into two different clusters. And then instead of modeling all these different kinds of tissues, we can just model two kinds of tissues. One class of water-based tissues and another class of oil-based tissues. Okay, so this reduces the problem complexity a little bit, because I don't have to model all these different kinds of tissues. But I still don't know what's the order and the number of these layers. And here we make a different observation. So essentially, so this is a lemma that I'm stating informally here, but we have a formal proof in the paper, and I'm happy to discuss more. But in general, the order of the tissue layers can be changed without impacting the location estimate if you design an algorithm that just uses phase of the wireless signal. So what this means is that I can reorder these tissue layers without impacting the location estimate. So I'm just going to demonstrate it by the simple example by reordering these line segments. But this holds true for like more complex cases. So I can reorganize these layers to put water-based layers together and oil-based layers together. And instead of modeling all these different kinds of tissues, I can just model two kinds of tissues, one water-based tissues and one thick layer of oil-based tissues. So now I just need to model two hyperparameters, one for the thickness of this muscle or like water, and the other for the thickness of this oil. And to do that, we can just use like additional constraints that stem from localization or from refraction, like the Snell's law, or geometric constraints of the human body. And by doing that, we can model the signal propagation and use localization methods to localize devices inside the body. So I told you briefly about the high-level ideas behind Remix. Let me quickly talk about evaluation. And actually, evaluation for these projects is quite challenging because we can't really put things inside the human body. So we have to come up with alternates. And we rely a lot on the medical community for their expertise on this. In the medical community, typically there are two different kinds of methods that are used to simulate this. One is to use animal tissues like chicken and pork, and the other is to create human tissue phantoms. So human tissue phantoms are just chemically synthesized tissues that have properties similar to the human body. And we try both. So this is a picture of our setup. We have a chicken. We put things inside the chicken, and this is our external transmitters, and we have 3 receivers for localization. So I'm just going to show two results. One is for communication, and the other one is for localization. And this is the communication result. On the x-axis, we have depth inside the body of it's up to 9 centimeters. So typically, the human muscle depth is 3 to 4 centimeters, and fat is 1 to 2. So this is actually beyond typical human depths. And the y-axis is the SNR. So yeah, so SNR is the signal-to-noise ratio measured on the log scale. If you don't have an intuition for this, typically the higher the better. And I'm going to compare two results: one for the human phantom and the other for the chicken. So this is the result for the phantom, and this is for the chicken. So as expected, as you go deeper inside the body, the SNR goes down. On average, we can get an SNR of about 15 dB across these experiments, which is sufficient to support data rates of about 1 megabits per second. And this can support like low resolution in-body cameras or other kinds of sensors inside the body. Yeah, so this is the localization result. And here I'm going to compare two methods. One is the proposed method Remix, which uses splines to model the human body. And the other is a traditional method that uses straight lines to model or straight lines for localization. And the x-axis is the localization error in centimeter, and the y-axis is the CDF. So this is the result for Remix. On average, we get an accuracy about 1.4 centimeters inside the body. The max error is about 3 centimeters. Just to give you reference, for in-body capsules, for example, the kind of accuracy required is about 5 centimeters, so we can achieve that here. If you were to use traditional methods that use straight lines, you will get much larger errors. The median is about 12 and the max is about 20. So of course, Remix is based on a large body of related work. So there is a lot of work in Backscatter, in-air, Backscatter that's been published at multiple venues. And I told you why that work differs from from in-body backscatter networks. And similarly, there's a lot of work in in-air localization, and I can tell you why that work differs from in-air devices. In the medical community, actually, there are some tools like PillCam and MicroCam, which are in-body capsules, and they rely on batteries to power themselves, and they use Wi-Fi. Typically, they are meant for very short-term specific applications, and they cannot last long because Wi-Fi is such a battery drain. And in terms of localization, typically people use X-rays, MRI, or CT scans for in-body localization. And again, in these techniques are both expensive and in some cases harmful for the human body. So we're actually very excited about, yeah.
So, I don't know too much about in-body capsules, but how do people think about storing images versus transmitting them? It seems like, storage is quite dense, and you could just store a bunch of images that you capture, and then as it passes through your body, you collect them at the end rather than transmitting them every time you take a picture. Is there a reason why people have focused on transmitting images as opposed to storing them?
Yeah, so specifically for images, I'm not sure because that seems to make sense for me, that you could store and pass them to the body and later transmit that data. But there are multiple use cases for this kind of work. For example, there are these devices that you can put in your gut and that monitor the pH for acid reflux, and those are typically long-term applications. And for them, transmitting makes much more sense because you want some real-time feedback. I'm going to show you one application just on the next slide, where you actually care about real-time feedback. So definitely in applications where real-time feedback matters, it's very important to transmit. Specifically in the case of images, I wouldn't know. One possible application, for example, is when you want to say deposit medicine based on an image, and there you wouldn't want to do some sort of real-time work. But again, you could send a capsule to take images and then later a capsule to
Yeah, I mean that's the sort of thing.
Yeah.
Clearly, there are applications you want in real time to monitor, but then there are probably other sets of applications where something is going to pass through your body, and you're going to do some analysis at the end of its traversal.
Yeah, makes sense.
For the layers, is there an assumption that they are uniform, or in terms of the thickness? Can
Yeah,
you
so that's actually a good question. Typically, so we use frequencies around like 900 megahertz. At those frequencies, anything that comes from inside the body has to come from like a very small region, because like the difference between human body and the air is very high. So basically, everything that goes out will just like reflect a lot. So what this means is that the escape region is very small, and within that small region, you can assume that they're uniform. Yeah.
In the previous evaluation slide, how did you get the ground truth?
For the location. Because it's like a dead chicken, we can poke it wherever we want. So we have like a fixed set of like coordinate frames, and then we can just like put it like at x, y within the chicken, and then we have like an estimate coming from outside. Yeah, sure.
So in a real world deployment, like what would the setup be in terms of the transmitter? Is there some sort of device that the patient would have with them in the home? You know,
Yeah.
What would it be pointed at their body? Like, would it be multiple devices? What would that look like?
Yeah, so you can think of like two kinds of applications. One is more like in the hospital. So there it's like a little simple that you put like something by your bedside, and that can give you like location, data, all of it. In the home, it's relatively less clear, I would say, because there can be like two different things. One is that you like wear a belt and it communicates with this and then transmits to like LTE or something. The other setup is like putting things on the wall, for example, and that communicates with this. In our setup so far, we've like the range between the device outside and the body is about 2 to 3 meters, which I don't think allows you enough mobility space in the home. But yeah, so that's what I would
in the
imagine.
hospital space, like how big do those devices have to be?
Yeah, so
Like,
I
you have
can
pictures of, like, different
so this
studio
picture,
forms.
yeah, so okay.
Well, no, before you go to that picture, so you're assuming that this object inside the body is static, not moving at all,
No, it is moving.
and you compensate for that?
So we are identifying its location, yeah. So we are finding both its location and we can also communicate with it. Both, yeah. So yeah, so this is actually a picture from Massachusetts General Hospital, which is like a hospital close to MIT, and there we're trying to use remix for cancer patients. And in general, one of the problems in cancer radiation therapy, or basically like overall the process of cancer radiation therapy is that you like deliver a high dose of radiation to tumor cells so that they die. But invariably, what happens during the treatment process is that these tumor cells can move because they can be like, for example, in the breast or the lungs, which move because of breathing. And so the radiation can hit those or like hit healthy tissues and miss the tumor cells just because of this motion. So ideally, you would want to have some sort of feedback as to the location of these tumors. And what we're trying out here with doctors is to implant small markers inside these tumors at the time of biopsy. And then as the tumor moves, you can track it using our system and then steer the beam along with it so that you hit only the cancer cells and don't hit any of the healthy tissues around it. Yeah.
Earlier you mentioned that the location accuracy was about 5 centimeters. Does it mean that you can track it and more accurately?
So our location accuracy, so I said the requirement for the capsule was 5 centimeters. Our location is like 1.5 centimeters. So typically, actually, the beam width of these radiation things is like 5 millimeters. So we would want to be better in that sense because like 1.4 to 5 millimeters is still like about a couple, like 2 to 3 or like 3 times better. We're trying, like we're working on that to make it better, but like this is also still better than what they have.
Can you contrast some of this work with, for example, the work that Fidel has been doing as well?
Yeah, of course.
Because when at the high level, they seem very similar to me, but obviously I'm missing the nuance here.
Yeah, so there are like, so I think like there is like the technical aspect and then the personal. So Father's work is like sort of parallel in the sense that we started at the same time, we like did different things. But specifically like, Father's work is more about how can we use existing RFIDs inside the body, and the answer is that you should transmit as much power as possible so that you can activate these RFIDs. We're sort of taking the flipped approach in the sense that how do you redesign these RFIDs so that you don't have to transmit a lot of power inside the body, but you can still get like enough communication inside going. And of course, on top, like our work is also focused on localization, which is not the focus of that work. That's mostly just focused on communication. Here, we're focused on both communication and localization of these devices. So in this case, for example, we can completely pass it, like without any battery, we can locate things inside the body. And that's like really required for this cancer radiation therapy work. So I don't know if there's a follow-up to that. Like, does that answer the question?
No, that's great. That's great. I mean, I'll go back and look, but for now, I'm fine.
Yeah, we can talk later. You know?
Yeah.
Okay. So yeah, are there like other questions about the in-body work? Because I'm going to move to the second axis of my work, which is this in context-aware smart homes. Okay. Yeah. So in the beginning of this talk, I told you that today we have to control all of these smart devices around us manually, and clearly that approach is not scale as we have more and more of these devices around us. Ideally, we want to automate this decision based on contextual information. We want to design smart homes that can truly understand our behaviors, our habits, our needs, and respond accordingly to them. For example, I gave you this example where if Bob sits on the TV couch, the TV turns on and tunes into their favorite TV channel. And this is just like one simple example. Smart homes can do much more. They can monitor healthcare of individual occupants. They can remind you to take your pills on time. And in general, they can reduce the carbon footprint of the home. And for all of these applications, the key primitive that they require is the location and identity of their occupants. So how do we get this contextual information? One option, of course, is to use cameras. But the problem with cameras is that you don't want cameras in your home. They're very privacy invasive. Clearly, I wouldn't want that. So what about RF? So we carry Wi-Fi devices with us all the time. We have smartphones. We have smartwatches that transmit Wi-Fi signals. So if we can find the location of these devices, we can use these locations as proxy for individuals. For example, if we know that Bob's smartphone is in the bedroom, then it's very likely that Bob is in the bedroom. And of course, there are cases when that's not true, and I'll talk about those cases later. But for now, let's focus on getting the location of these Wi-Fi devices. And as you know, there is a lot of work in RF-based localization and also in particular on Wi-Fi localization. But most of that work actually focuses on enterprise settings where they have 4 to 5 access points covering the same location. But the problem is that in our homes, we don't have as many access points. We don't have this extensive deployment. We typically have just one Wi-Fi access point. So the question that I'm going to ask today is that how can we use this one access point that we have in our homes to locate Wi-Fi devices accurately? And before I tell you that, let's take a step back and try and understand why past work requires multiple access points. So typically, as I just showed you, this is how RF-based localization would work. So you have a device that you want to find the location of, and then there's an access point where you can use the multiple antennas to compute an angle to this device. So you just get an angle, and then you get this from multiple vantage points, intersect them, and get the location. So what if I tell you that I want to do it with just one Wi-Fi access point? What extra information would you need? So we already know how to compute the angle. What extra can I give you to give you this location? Of course, distance. So if I both have the angle and the distance, I can use them to find the location of this device from a single vantage point. And the next obvious question is, how do we measure this distance? So Wi-Fi signals are electromagnetic waves that travel at the speed of light. So if I can compute the time that it takes for the signal to go from this smartphone to this access point, I can just multiply that by the speed of light and get the distance. But the problem is that the speed of light is very high. So if you want to do it reasonably well, you have to measure this time very accurately. And in fact, you need to measure this to about a nanosecond accuracy. So 1 nanosecond in time is about 30 centimeters in distance, or like 1 foot. So that's about the accuracy that you need. So you need to measure this time to an accuracy of a nanosecond. And as we know from basic signal processing, time resolution is inversely proportional to signal bandwidth. So if we need 1 nanosecond resolution, we need 1 gigahertz of bandwidth. But unfortunately for us, Wi-Fi devices today transmit much lower frequency, so much lower bandwidth. So they transmit 20 or 40 megahertz of bandwidth, which is 25 to 50 times lower than what we actually need. So the key idea behind this work is that even though Wi-Fi signals transmit at one particular frequency band at one point of time, they have the ability to switch frequencies. So remember, when you buy these Wi-Fi routers, when you set them up, you have the option to choose a channel. And each channel occurs at a different frequency. So if you can stitch together information across these multiple Wi-Fi bands that they're capable of transmitting at, we can emulate a bandwidth which is greater than 1 gigahertz. So this is the high-level idea. Let's see how we can do that in practice. So for this, we're going to use the phase of the signal. So wireless signals have both an amplitude and a phase. And the phase of the signal is connected to this time of flight by this equation here. So it's phi equal to 2 pi ft, where f is the frequency, mod 2 pi. So if I can measure the phase of the signal, I can just plug it into this equation here, and then get multiple options for the time of flight, because this is mod 2 pi. So I measure the phase at, say, at 2.41 gigahertz, and then I get multiple options for the time of flight. And how do we select between these multiple options? Well, we have multiple frequencies, and all of them are going to have different modulo factors. And as a result, I can just pick the one where all of them agree on. So you can just use this like a simple Chinese remainder theorem to solve this. Okay, so this is, again, still very high level because Wi-Fi signals don't just transmit and receive along one single path. They're going to reflect of multiple things in the environment, of the ceiling, of the floor, of all this like walls. And as a result, there are multiple paths. So there's not just one time delay, there are multiple time delays. And I'm interested in figuring out actually all of them. And then to pick the direct path, what I can do is I can just pick the shortest of them because the shortest path is always the direct path. So to identify all of these paths and this distribution of the time of flight, we have this sparse inverse Fourier transform formulation. So if you are not interested in the math, just zone off for like a minute, and I'll briefly go over this, and then I'll come back and I'll not use this again. So essentially, this is the signal phase that I showed you here. You can write the signal in the Euler form based on this phase here. And then because there's multipaths, so the signal is just going to be the sum of the signal along different paths. So we get an input, which is the signal measurement at n different frequencies. And we need the amplitude for each of these delays. So we can get a distribution of these delays. And we can formulate this as a L2 norm optimization problem. But the problem is that Wi-Fi frequencies are not uniformly spaced. So this formulation is underspecified. So we have to use additional constraints. And we can use sparsity. So this is an L1 sparsity term that enforces sparsity and forces it to pick solutions that are sparse from this ill-defined problem. And by doing that, we can get delays for each of these paths and pick the shortest path. So I'm going to very quickly show you the localization accuracy that we achieve by doing this. And this is just one quick result. So the x-axis is the error in meters, and this is like a typical space of about like 10 to 15 meter distance. And the y-axis is the CDF, and I'm going to show you a result for line of sight and one for non-line of sight. So for line of sight, that is when there's line of sight between the transmitter and the receiver, we can achieve a median accuracy of about 65 centimeters. For non-line of sight, when there's no line of sight between the transmitter and the receiver, we can get an error of about 98 centimeters. And this is using just one device. So in contrast, the state of the art in Wi-Fi localization, which is SPOT5, this paper called SPOT5 from SIGCOMM 2015, achieves a similar accuracy using 4 to 5 access points. And we can do that because we can stitch information from multiple Wi-Fi frequency bands together to get access to distance in addition to just the angle. So yeah. So I very quickly told you how we can use this single Wi-Fi access point in homes to locate Wi-Fi devices. But is that enough? Clearly not, right? Because we don't always carry our phones on ourselves in our homes. I might leave it in the kitchen, walk to the bedroom, or leave it in the living room and walk to the kitchen. And that happens a lot with you guys as well. And in fact, there are people who study this phenomena a lot, and they found out that about 50% of the time, people don't carry their phones on them in their homes. So what we have done is we've solved just like 50% of the problem. So we have weak indicators of where people are, but this is true only for 50% of the time. What can we do for the other 50%? And to solve for the other 50%, I'm going to use a different mode of localizing people by using reflection. So again, this is past work. This is not what I do. But in general, this line of work says that you can use reflections from the human body to track people. And on a high level, this is how it operates. So let's say there's this device. It transmits a signal. It gets reflections from this person. And then by carefully processing those reflections, it can tell you where the people are. And the good thing about this is that you don't really need people to carry devices on. But the bad thing is that there's no notion of identity. That most times, these reflections are very weak. So signal from me looks very similar to the signal from you. So we have this interesting dichotomy that on one hand, we have these device-based localization systems that need people to carry devices, but they can identify people. And on the other hand, we have these reflection-based localization systems that don't need cell phones, but they cannot identify people. And clearly, we want the best of both worlds. We want to be able to identify people, but we don't want them to carry their smartphones on them all the time. So we're going to use both. So we're going to track both people and devices and use the interactions between them to match. So on a high level, this is what we're going to do. So we're going to get a trajectory which does not have an identity from the reflection-based system. And then we're going to track devices based on this device-based system. And we're going to compute the overlap between them into this parameter called the interaction score. I'm going to just roughly define it here as an interaction score. So what this means is that let's say we have two people in the home. We don't know who they are. There's someone in the bedroom and there's someone in the kitchen. This person in the kitchen walks out, starts interacting with their smartphone, and we can tell that, oh, this person is Bob because they're interacting with Bob's smartphone. And then we can make this identity sticky because now that we've identified them, we can keep tracking them as Bob later, and we can also see that the person who was in the kitchen was Bob in the past. So what's the problem? Well, the problem is that this is still a very weak indicator because I'm not the only one who interacts with my smartphone. Sometimes my wife will come and start playing with my smartphone, or me and my wife are sitting together and we are interacting with our own smartphones, but the error might match them to different people. And the other problem is that there is missing data in the sense that these reflections from the human body are very weak, so they can be easily blocked by things inside the home. For example, bathroom tiles, TV, fridge, etc. And as a result, we might stop tracking individuals in some locations, and when they reappear, we lose track of their identity because we don't know who they are. So how can we solve this problem? Well, think about it. Intuitively, we already thought how we could solve this problem because we know that people don't appear, disappear, or reappear out of nowhere. We know that because this person who went to the bathroom was Bob, anyone who comes out must also be Bob. There's no there's object permanence in that sense, right? So we want to embed this human-level intuition into the design of the system that can reason about such intermittent information. And the second idea is that we can combine information over time. So even though my wife might interact with my smartphone at one point, she'll later go and interact with her own smartphone. And we can combine these multiple weak interactions to build a strong indicator of who this person is. So we can formally specify this into a first-order logic formulation that can track the state of individuals. So it represents state in this variable called st. And there's a belief in each of these states, which we track as probabilities of who these individuals are. And each state has multiple variables. So each variable is a person that we are tracking. And each variable might have different constraints. So there are 3 constraints, P, I, and R. And P is the possible identities for the individual, that this person is either, say, Alice or Bob. I is the impossible identities for the individual. So we can have constraints like this person is anyone but Charlie. And R is the location of the individual. So it's like the bed, bedroom, kitchen. So the nice thing about this formulation is that we can reason about a very rich set of constraints. We can have constraints like this person is either Alice or Bob, but not Charlie. We also have a provable validity algorithm that can check validity of each of these states and prune out invalid states. So it can enforce logical rules like the people cannot be present in 2 places at the same time. They cannot enter places that they already occupy, and they cannot exit from places that they don't occupy. So we built this system, we implemented it, we deployed it in 2 different studies in a home and in an office space. During these studies, occupants used their own smartphones. They did not really have to install an app. They just had to do a one-time registration with the system to give consent and to give us their MAC address so that we can associate a MAC address to an identity. And it required no changes to the user behavior. And for ground truth, we used cameras in both of these spaces. So I'm just going to show you one result about the home and not focus on the office as much. So the home is about 13 meter by 9 meter space. It has 2 occupants and 2 frequent visitors. It's an apartment on MIT campus. There are 2 bedrooms, a bathroom, a kitchen, a living room, and a couch. Okay. And I'm just going to show you the accuracy number. That's the percentage of time that we got both the location and identity of individuals correct. And the y-axis is that accuracy in percentage. And on the x-axis, I'm going to compare 2 schemes, one that just uses a device, that's the device that people are carrying for the location, and the other that uses device plus reflections and also augments it with the logical reasoning framework. So as you can see, if we just rely on the device, we get it right about 40% of the time. But this can go up to about 95% if you augment it with reflections and the logical reasoning framework that we built. We can actually zoom into this a bit more and look at location-wise accuracy numbers. So the locations that we are tracking are bathroom, bed, kitchen, bathroom, and couch. And across these locations, we get very high accuracies. The couch is a bit lower because there can be multiple people sitting very close to each other on the couch. Yeah.
So a question.
Yeah.
What type of access point or transmitter were used in these experiments?
So the device. So basically, we are just using our own smartphones for people. For external devices, we are using like an Intel Wi-Fi card. to track devices because it gives us access to phase information in addition to just the RSSI information, and we are using a custom built device to track people, like reflection-based people. So essentially, there's actually like work that has happened after this that has been able to track people based on like custom non-custom Wi-Fi cards, basically just using like off-the-shelf Wi-Fi cards. But we used like a custom thing because we already had that in the lab. Yeah.
So thinking of this from a security perspective, if somebody, I don't know, gains access to my access point, does that then allow them to track individuals in the home? Or how difficult would such an attack be to launch?
Yeah, so I would say a coarse-grained location is definitely not hard at all. Like I feel like if someone would gain access to like your access point, they could definitely like track your coarse-grained location.
So what does coarse mean?
Yeah, about like a couple meters, I guess. Yeah, sure. And like you can get finer, like if you have like access to like the phase information, then it gets more finer over time. So it's just that. So I think there are definitely like security implications of that, and there are like ways to circumvent or to build security mechanisms around this. I don't think existing systems do that. But there are definitely ways and depending on like what your attacker model is, there are like different methods that you can use.
And if let's say my attacker is the apartment next door, could they also do this? Will they have full control over their own access point?
Yeah. So again, it depends on like what your security model is. So let's say I'm your neighbor and I'm the attacker. But at the same time, I don't control like the software of my device. I just like bought a software, bought an access point, and I put it here. In that case, as a system designer, you could put safeguards simple challenge response mechanisms that to be tracked, you have to walk like 3 steps forward, 3 steps to the right, and that gives you some sort of consent as to like what tracking means. Now the other kind of attacker is like a PhD student at MIT who knows how to like program these devices. They know like phase information, everything. Yeah. So let's say assume I'm the attacker. And in that case, I think security is more challenging in the sense that you have to one way to enable security, for example, is to deploy an undergrad student at MIT who builds a system that spoofs these locations. So again, this is based on reflections, right? So if I put a small device here that spoofs like random reflections all the time, then like everything just goes down the drain. So this is like a security by obfuscation kind of thing. Yeah.
You also mentioned that the user has to register with the access point. So if someone next door has the access point, unless you register with it, it's not going to associate.
So the registration is like very lightweight in the sense that we just need to know like the MAC address that's associated with you. So if I like see you like walking out of your door once, then I know that okay, like the access point that walked out of your door is like you. So that's it.
It's not like an active registration.
Yeah, it's not really an active registration.
This is more like a permission.
Yeah, it's more like a permission. So sure, yeah.
I just wonder, what if like somebody, I don't know, a guest or a friend or something who comes into the home, you're getting the reflection and that mess up.
Yeah, so typically in this case, like if they're not registered, we track them as like unknown 1, like unknown 2. So we give them like fake IDs and we track them over time because they'll also carry some devices on them typically.
Also, what if they're like a dog or something?
Yeah, so dogs are a little bit harder in that sense, like especially if like my advisor has a dog. Dogs are definitely harder in the sense that they will have reflections, but they will not have devices. Like kids, for example, will have that, like reflections but not devices. Again, we give them like fake IDs and we try to eliminate them, but sometimes they will mess up with the system and reduce the accuracy. Yeah.
Is there a limit how many you can track?
So far we I think in. So let me be a bit clear about this. So in this case, in the home we had up to 4 occupants. In the office we had up to 10, but simultaneously we never had like more than 5 or 6. And that's what we believe is also probably the limit. Like 6, 7 is probably like what it works best for. Victor.
I just have a comment, not a question. So I'm going to date myself, but people already know how old I am. But in 1998.
Yeah.
I wrote a paper which uses Kalman filtering, modified Kalman filtering to figure out the state of the object at that time car's next state. And then use a Markov model to sort of figure out what are the actually legitimate states that one can actually be in and computes the transition probability. Effectively, it does very similar things in terms of like the Markov model encapsulates all the constraints that you talked about in terms of walls, and the Kalman filter actually says what So it's not just if you ever thought or even knew about that.
So I think this is actually like very similar to that in the sense that we use Kalman filtering to like filter trajectories. Then we use like a Markov model to track states. The thing that we're doing on top is we also have a logical reasoning framework that can prune out like valid and invalid states. So there is like a validity check on top of each of these states in addition to the Markov model itself. And the Markov model is like more generic in the sense that it can send you to like invalid states. But then the state validity check happens in the logical reasoning pipeline. I think the nice part of that is that you can enforce rules like arbitrarily. Like you can have like a rule of like how your world should look like, and those rules can enforce like your state validity checks.
But who writes those rules?
So here they are like hand coded. They are not like inferred, for example, by using like a deep learning mechanism. No, they are hard coded. Yeah. So like more traditional AI. Yeah.
So, in terms of the reflections, did you investigate whether it might be possible to sort of generate a personal signature of reflections or something?
Yeah, so I haven't, but there are other people who have. And in general, it's like the answer is not clear in the sense that like just using like reflections alone, it has like, it's not possible. But there are other features like gait of the person, for example, acts as like some sort of pseudo sign. So over time, like if you combine these features, like behaviors, like right, like if I like track you for a day, I can probably tell it's you versus someone else. So these are like over long-term patterns, you could get some notion of identity. Yeah, short-term, I think it's still not clear if it's possible or not possible. Yeah. Okay, cool. Okay, so. Yeah, so I talked about in-body networks, context-aware smart homes, and now I'm going to very briefly talk about data-driven agriculture. And I know a lot of you have heard this already from like different people. I gave an intern talk here, like I'm sure Ranveer talked about here, but I'll just like very briefly touch on this. So essentially, the objective is that we want to work on the agricultural challenge, that the agricultural output of the world needs to double by 2050 to meet the growing demands of the population. But at the same time, this is challenging because water levels across the planet are shrinking. We don't have enough arable land, and at the same time, we are facing climate change. And as a result, the crop production of the world is expected to go down over the next few years and not up. And this has been like a very hotly debated topic in the agricultural community. And one of the most promising techniques today is something called data-driven agriculture. And on a high level, this is what data-driven agriculture means. So in traditional farming, if I give you X amount of water, you take this water, apply it uniformly across your field. And actually, this is a picture from a farm close to here, like a 20-minute drive. But yeah, so in traditional farming, you take X amount of water, you apply it uniformly across the field. But what data-driven agriculture says is that that's not the right way to do it. Instead, what you should do is measure the amount of moisture in each part of your field and then treat it accordingly. And you can do it for other kinds of farm inputs like moisture, pH, nitrogen, fertilizer. And by doing that, you can improve your yield, reduce the cost of agriculture, and make it more sustainable. So that's great. There is a problem that we need more food, and there's a solution, data-driven agriculture. What's missing? And well, the problem is that collecting this data is very challenging because we have very limited resources on the farm. Ideally, you would want to deploy these sensors all around the farm and collect data from them. But the questions are, how do you connect to these sensors in the first place when they are located in rural areas that don't have regular modes of connectivity? How do you power these sensors when you have non-reliable sources of power like solar or wind, which are very weather dependent? And in a place like Seattle, you can tell that you can't really rely on solar power all the time. And finally, while you would want to deploy a lot of these sensors, it's not really feasible because A, it's expensive, and B, it's logistically infeasible for the farmer. A farmer has to drive a tractor around this or a bullock cart, and if they're going to run into these sensors all the time, it's just not going to work. So I'm not going to go into the details of the solutions, but just like one of the very high-level ideas behind FarmBeats is that we can reduce the number of sensors that are required on the field by combining multiple modes of data together. So we combine visual data from a drone and ground sensor data from these sensors, and we can create measurements that are as dense as putting those sensors without requiring a dense deployment. And on a high level, this is how it works. So we send a drone to take a video of the farm. We combine that video into a panoramic overview. And then we combine it with sparse sensor data on the field to create dense sensor maps that look like this. And generally, this is a simple machine learning formulation. We have these sensors that operate as training data, and we can predict on the rest of the farm based on a model that we can learn from this data. And we build like a Gaussian process model to formalize this. So we have input features that are coming from the drone. These are visual features, which are xi. You want to go to the output, say moisture, temperature, or pH, yi's. And there are two kinds of constraints that we model. One is visual similarity, that areas that look similar to each other should have similar sensor values. And the other model is, the other constraint is spatial smoothness, that areas that are closely located in space have similar sensor values. And we can learn these constraints or the kernels W and K in the training phase. And in the test phase, we can use these kernels to generate outputs for unknown areas. And by doing that, we can create these precision maps of the field. So this is actually a pH map, and that's a moisture map. The pH goes from a scale from like 4.5 to 7.5. 4.5 is very acidic. 7 is about neutral. So you don't want your crop like field to be too acidic when you are planting some crops. In this case, you could tell the farmer that this part is more acidic than they would want them to be, and they could take action before they planted those crops. And similarly, this is the moisture variation from 1 to 4, where 1 is dry and 4 is moist. So this is actually a picture of our first deployment. This is very close to here in Carnation. We deployed it here. This picture, like I like this picture because it shows like the challenges that exist on a farm. One is that this is like an area that's secluded, does not really have regular forms of connectivity. They are surrounded by crops and canopies, so signal does not really travel through as well if you're operating at higher frequencies. Again, and solar and wind power is weather variable because of the base in Seattle. So we could say that there were several days we did not get like enough solar output to power these. And to make the system like more available, more reliable, in spite of these challenges, is what forms the crux of FarmBeats. And I'm happy to talk more about it later. But I guess you've heard this around a lot of the times. So now FarmBeats has evolved to be a platform, and actually farmers write their own application sometimes. This is a cool application that I really like because they're tracking their cows using a cow neural network. Yeah. So over time, so we started out here and here. So we had a deployment in Essex Farm and in Carnation in our first year. We started in 2015. Over time, we have had more deployments, like more in India, actually one in Africa and New Zealand. And some of these deployments have been in operation for a couple of years, and farmers have reported increased yields and reduced inputs by 30 to 45% in these deployments. So, yeah, I don't have to say it here, but there was a private preview that was released in January 2019, and there's going to be a public preview this summer for FarmBeats. We got a good amount of attention from people here. Satya called our project one of 10 projects that inspired him in 2017. Bill Gates recently visited a FarmBeats deployment and blogged about us. So yeah, so today I talk to you about my work in building IoT systems in very different domains. Even though I focused on just one axis for each of these problems, actually all of these.
You didn't actually tell us what you did in the FarmBeats.
Okay, yeah, so.
You don't have to show pictures, just tell us.
Okay, so I can tell you what I did in the FarmBeats project. So I started with FarmBeats in like 2015, which is when like we started FarmBeats together. We were like a group of 4 interns. The project, so like I contributed to multiple parts, but one of my core contributions was the pipeline that I just showed you, which is the. So I did 2 things. I designed the edge, which like basically brings everything together and runs all the algorithms. And I also designed this machine learning pipeline that puts like a vision and a machine learning pipeline that takes all of these sensors, takes this drone video, and combines them together to generate these precision maps. Yeah.
Do you know what the accuracy drop is of your precision maps?
What's the
versus ground truth?
What's the accuracy?
Yeah, what's the accuracy drop there? Having dense sensors.
Yeah. So typically, like in our experiments here, we found that the accuracy drop is not very significant in the sense that it is within the error margins of the sensors themselves. So the sensors have like a least count of like 1 or like 2 degrees Fahrenheit, for example, for temperature. We are within that. For pH, I think it's about like 1.5 times the least count. So it's like within the error margins of the sensors themselves. Yeah.
Did the weather conditions affect? Like you're taking images to train and identify data, right? Like air quality, like just air conditions and weather conditions, did they affect how it performed?
Yeah, so I think that's a good point, and that's also like why we have these sensors on all the time. Like so essentially we're not really like training today and testing tomorrow. so as to say, basically when the drone takes a flight, we get an image, but at the same time we have the sensor data. So these ground sparse sensor data can calibrate for like the air conditions, which is actually like a key difference between like what we do and what you would do like using a drone itself. Like if you just use a drone, like, that would be a problem. But if you have these sparse sensor data, they can calibrate for those kind of methods.
Does sensor bring up the problems with the tractor? Like, I know it's less, but still they have the same issue.
Yeah, so typically, like, we have markers around the sensors so that people don't run into them, and I don't think that has actually been a problem so far for us. Yeah. Okay, so in these cases, I talked about just one axis in each of these, but again, like all of these axes come together in each of these problems, and there are solutions along each of these axes. That's all about my past work. In the future, I'm actually very interested in working in the wireless networking and IoT space and progressing the state of the art. And I want to do that along two axes. One is along the methods, and the other is along the domains that we deploy these methods in. In terms of the methods, I'm very excited about the potential of machine learning to revisit or like to reinvent some of the methods or some of the problems in communication and localization. We've seen that one of the major challenges for wireless systems is to model how these signals are interacting with environments around us. And these are very complex interactions that are hard to capture using hand-coded methods. We have seen like machine learning has had a lot of success in domains like natural languages and computer vision in modeling these complex interactions. If we can translate some of that work to wireless networking, we can solve new problems in communication. For example, link establishment in next-generation cellular networks that use millimeter wave, or scheduling problems in the cellular networks. In terms of sensing, I'm actually very interested or very excited about the potential of our smart devices like our smartphones. Our smartphones transmit multiple different frequencies today, like 2 gigahertz and 5 gigahertz for Wi-Fi, 2 gigahertz for Bluetooth, 100 megahertz for NFC, and very soon they're going to transmit like 20 and 80 gigahertz for millimeter wave. And these signals have very different interactions with our environments. If you can combine these sensing powers with the modeling power of machine learning, we can think about sensing new kinds of things, like the materials around us for augmented reality and virtual reality, or the safety of food and water that we consume. In terms of domains, I showed you some of my work in the digital healthcare space. I'm very excited in continuing a lot of that. Today, I showed you that we can communicate with these devices without requiring them to transmit any power, but where can we take this a step further and remove all batteries altogether by using some of the power harvesting work in addition to just this backscatter work that I was talking about. Also, I showed that these signals have very different interactions with different kinds of human tissues. Can we model these interactions and infer properties of human healthcare? For example, can I predict brain strokes before they happen, or think about prediction of early onset Alzheimer's based on, say, like a cap that I'm wearing with antennas? I also have some work in smart cities that I did not get a chance to talk about today. But going forward in the future, smart cities are invariably going to have mixed traffic that have autonomous vehicles and human drivers at the same time. What kind of communication and sensing infrastructure do we need to support such kind of mixed traffic? Can we enable autonomous vehicles to look around corners based on this communication infrastructure? And can we enable them to see through dense fog and smog even though camera visibility might be low? And of course, underlying all of this work are concerns for security and privacy. These concerns have become much stronger of late, and they're actually becoming stronger. I cannot help but admit that my work raises some of these concerns themselves. I showed you that we can track people without requiring them to change their behavior in any way. So first of all, how can we detect that a simple Wi-Fi router sitting in the background is tracking me all the time? And how can we build shields that prevent such kinds of tracking? And of course, how can we integrate this physical information into the overall security design of IoT systems themselves is something that I'm interested in. So with that, I will conclude, and I'm happy to take more questions. Victor, you have more questions?
Yeah.
Sure.
Yeah.
No, we have time. Go ahead.
Okay.
Sure, I have a FarmBeats question. You probably got this question before, but okay. So when your drone is capturing visual information, do you have to worry about things like shadows and other sorts of visual artifacts that are temporary affecting your inference? in a large field, maybe there aren't very many shadows. But maybe as the crops grow, there are shadows at different angles. Did you ever encounter issues with things like that?
So typically, the shadows are very tiny, that they don't seem to matter on the large scale. Specifically for a single location, I really can't say for sure. If for example, if I have a shadow falling here, does my value here change? We haven't really investigated that. But on the overall scale, small shadows here and there don't really seem to matter that much. So that's.
With orchards at all? Because I imagine it would be a bigger problem with actual.
So typically, I think we work with cabbage or lettuce, and then different kinds of potatoes, for example.
Root vegetables is not a problem.
Yeah. So with orchards, I would imagine, I would know. We haven't worked with them. Yeah.
Do you need to have visibility of the ground, or is it following up from lindens? If there is a larger bush, or in lavender farms, there's not really much you can see under the shrubs.
Yeah.
Do you need information?
So again, I think as the project is evolving, so I can tell you what this is and what we're doing now. So essentially, in this case, you do need probably some visibility into the ground, but crops also have some sort of signatures that this system can capture, because again, this is model free in that sense that it'll capture whatever the data suggests it does. But increasingly, we are also interested in more things in the spectrum going into this model. For example, this was just RGB cameras. We've also tried to use NIR just by removing the filter. And probably going forward, we'll also use some RF sensing data and combine it, and that will probably give us a more holistic picture than what this gives us already. Yeah.
So it's kind of an unfair question to ask, but that's why I was wanted to do it in private. Okay, anyway. So in going back to FarmBeats, for example, so you have this notion of sensors that are placed, right?
Yeah.
Now these sensors have to be battery operated, they have to have communication ability, or alternatively you just you have this other sensor, which is the drone which is going, and you've got the imagery going on. And when the drone is going on, it's moving around quite a bit, so you sort of you have to stitch all that stuff together properly, and it's not clear how you potentially do that. And even if the drone is going, then you're sort of taking into account the cameras, the ability of the camera to be able to see. And the questions were asked under the surface of the shrub, in the ground, how much groundwater you have, things of that nature. So it sort of seems to me that I don't know how much of this you've actually really solved. So in the sense of again, put the sensor on the ground and then you have to communicate, right?
Yeah.
How much of that is actually real?
So
you want to communicate it, you talked about the edge, so I'm assuming there's nobody in the farm at the time, so that's being uploaded to somewhere else, and the British time to sort of look at that.
Yeah. So again, this project has a lot of components, and it continues to evolve. But the problem around communication is definitely very stable at this point. That we can communicate with sensors on the ground, can communicate to the edge. That design is very stable.
How's the battery? How much battery do you have? How long does it last? How often do you have to go and change those?
So again, so this is the you asked what I worked on. So this is the other part of the project that I worked on. Is that so it has batteries, of course, and then those batteries are are rechargeable, so they recharge with solar power. But one of the things that we looked at also is that basically solar powers have very weather dependent. They're very weather dependent, right? That it can be cloudy tomorrow and your sensor would go down. And if you want data for tomorrow, then you want to preserve energy for today. So we use weather forecasts to predict these solar power outputs, and then use them to duty cycle these sensors accordingly, for example. So that's one of the things that I did. But that helps us, for example, operate sensors even when they're low on battery, or when they're not going to get enough solar charge tomorrow. So there are these modules. The other kind of modules that not me but other people have built are on identifying which of these sensors are giving out wrong values because they are broken at some location. And in terms of the communication, we use white spaces or LoRa for the sensor to the edge, and then the edge communicates using a standard a connectivity module that can be in a farmer's home, or in case of India in a village. The other kind of challenges that we've looked at are also like with drone regulation, for example, that here like using drones is easy. They are relatively cheap for farmers, like farmers can afford them. In India, like farmers cannot afford drones, and like drone regulation is also not clear. So we use like helium balloons with cameras on them to like walk, like these are like tethered drones, so as to say. So these are the other challenges.
Yeah.
So
answer to my battery question was rechargeable solar.
Yes, rechargeable solar.
Okay, that's a little.
That's true. Right.
Depends on how much battery. Let me step back and ask you, what is your thesis?
I see.
What is the thesis statement that you have when you look at all these different pieces of work that you've done?
Yeah, so I think one of the like core contributions of my work is showing that how can you take like essentially how do you build like IoT systems in resource constraint settings. So in-body is like a resource constraint setting, like on a small scale, and farms are on the large scale, and then cities and homes are on the medium scale. So this is like at varying degrees of scale, how do you enable IoT systems in resource constrained environments? So that's my thesis.
And these techniques that you've talked about, you feel are going to last the test of time, or things that are variable. Like that's why I sort of.
Yes.
But then the thing with the FarmBeats, I think the first part, it seemed like that to me. It seemed like you have something.
I see. So your question is like, is this specific to FarmBeats, and is it like some specific to everything else?
Yeah, the FarmBeats, I'm not sure whether you've gotten it yet, but I think the other two probably.
Yeah. Yeah, again, this is like a broad philosophical like answer and also a question in the sense that I see these projects as evolution in the sense that they evolve to like be more mature and over time. So the localization work is like more mature in that sense, right? That like you started it like 20 years ago, and now I'm like building on that work and continuing that line. And of course, it's more mature and it's going to like have more impact. The in-body work is like something that we started like 2-3 years ago, and as a result, it is less mature, and of course, some of these techniques will last the test of time, and some of these things will be like overtaken by something else. Honestly, I would like to believe that they would last the test of time, but again, because as the work matures, like as more people work on it, like it will become like more mature, more deployable. Like we will work on it, other people will work on it. I feel it's similar for FarmBeats in that sense that like. Enabling data-driven agriculture is a big challenge. It's not something that I would expect to solve in a single paper. And we believe that some of the solutions that we have are pretty fundamental to what you would do eventually. For example, like using weather forecast, like duty cycle, these systems is something like really simple and something that you would expect to do in such scenarios. Other things, for example, like using like drones and combining them with sensors. Probably you want to improve them, and that's what we're trying to do, right? Like using like radio signals or using like NIR imagery in addition to the imagery that we have. And again, there are questions about like how deployable is it, because when you want like additional hardware, like it becomes less deployable. So if you were to use like satellites, it will be like better, but like satellites are not as fine-grained. So how do you play that game? And there is not like a single solution that will operate across the world and across all the farms probably. And we continue to evolve basically. Like as we see more scenarios, more deployments, we evolve. And that's probably like I don't know how satisfying that answer is, but it's what the answer is. Yeah.
So like in the FarmBeats work, what's the fundamental cause for the difference in, let's say, moisture across the farm? Is that because of like sloping or something?
Yeah.
I'm just thinking like if there's certain causes that are due to geography or topology, then you could potentially just like train up front and compensate for that instead of like needing real-time feedback all the time.
Yeah. So again, I think it depends very much on like different factors. So one like sloping is one, for example, for moisture, but for nitrogen or like, it can depend on like how like distributed your fertilizer was, how close to the edge it is, because like maybe your like neighbor is doing something else, and like that gradient is like leaching onto you. So there can be like multiple different factors. I think your suggestion in general is is very good in the sense that if we can identify these parameters and control for them later, it's probably easier than doing it So that is a good point. So again, it really depends on the application. That for some applications it would not, and for some like others it would. So one application that I have in mind, for example, is detecting the amount of crop that was touched by flood water, for example. So this is just so there's some flood water. If it touches the crop, the farmer has to discard that crop. And now, doing a more fine-grained estimation that already exists is definitely going to save the farmer money. And those kind of problems, I feel, are less predictable in that sense because sort of some randomness that comes from the weather and all of this. So those things would probably need more sensing than less. But for say irrigation maps, I would imagine estimating the slope would work very well. So yeah.
Predictable, the farmers would learn themselves.
Yeah, that's what I was wondering, but maybe the time scale.
Yeah.
I mean, maybe there's some time scale which is not daily, but and not one time, but once a month or once I mean, it just seems like it would save cost in some sense.
Okay, I think this is very good.
Okay.